Welcome back to the last Quantum News monthly video of 2023. I'm your host Devo.
And I'm your co-host Mingyu. It's been our pleasure making these videos about quantum science for you in 2023, and we're excited to finish strong with some pretty big events in the field.
First off, IBM has released their first 1000 plus qubit chip, Condor, and Chinese tech giant Alibaba has just shut down their quantum computing wing.
Trapped ion quantum computers have been used for two impressive studies of fundamental quantum physics, one by our colleagues at Duke and the other by scientists at Innsbruck.
We'll check out what is up with this logical qubit paper from Harvard that Nature has released for an accelerated preview. And then we'll swerve into NASA's awesome cold atom experiment that they have in space.
Lots of ground to cover, so let's get started.
This month, IBM announced two new processors named after birds, Condor and Heron. Now, Condor is their biggest quantum processor yet, with 1,121 qubits. With this processor, they've really pushed the envelope on how many qubits they can fit in a single chip. And with Heron, they focused on getting really high-quality qubits that they can fit in a modular architecture. The Heron has 133 qubits, and compared to its comparable-sized predecessor, its gate errors are 3 times better, and gates are much faster. Because of improvements in both fidelity and gate speed, the Heron should be able to run over 9,000 coherent gates, which is also 3 times more than its predecessor.
What does the scouter say about its power level? It's over 9,000!
I'm really happy to see IBM's innovations in quantum technologies and their commitment to creating high-quality quantum processors that fit into modular designs. And also, of course, the 1000 plus qubit device is a great accomplishment. Good job. I do want to see more data on this device, especially randomized benchmarking. Moving on. While IBM has been doubling down on qubit count and qubit quality, the Chinese tech giant Alibaba is closing their quantum computing lab altogether after being in the quantum computing market since 2015. The company is going through some massive reorganization, and this could have been part of it. There's a lot of speculation as to why, and I read somewhere that the company is maybe refocusing on AI and machine learning, which makes me wonder, did I choose the right field, Mingyu?
Well, probably, but we love quantums though, so we'll stay in this field.
Yeah, no, we love this field.
So next up, I'm excited to introduce two papers on quantum simulations using trapped ions that were published in Nature this month. The first paper is from a team of our very own Duke University, showing something called the continuous symmetry breaking. It sounds like a handful of difficult words, but I'll break it down for you, so hang with me there. So first, what is symmetry? To define symmetry, first we need a physical system, and second, we need some kind of a transformation. For example, let's say we have a one-dimensional chain of particles, and each particle has something called the spin that has a certain direction. And for the transformation part, there are many kinds. You can have discrete transformations, like particles altogether moving by one step, or flipping the spins by 180 degrees. And also there are continuous transformations, like particles sliding all together, or rotating the spins by any degree. Okay, now, let's say a system's property, like energy, doesn't change by doing such a transformation. Then we say that the system has a symmetry with respect to this transformation. And of course, if the transformation was a continuous one, like sliding or rotating by any degree, then the symmetry is a continuous symmetry. So finally, what does it mean to break a symmetry? Suppose your system originally had symmetry with respect to, let's say, this spin rotation. And that means that your system's energy doesn't change when you rotate the spins. And now imagine, for example, adding a magnetic field on a certain direction. Then the system's energy now depends on the spin direction. If your spins are aligned with the field, then you have less energy, but if your spins are in the opposite direction, you have more energy. So now energy does change when you rotate the spins, and that is symmetry breaking. Adding the magnetic field broke the symmetry.
If you're a physicist, you'll hear about symmetry breaking all the time. Even the Higgs mechanism, which is behind the famed God particle, is created by this symmetry breaking. So basically, we can have mass because of this symmetry breaking.
That was a long intro. Now back to the paper. Remember that the example system I just described is a one-dimensional chain of particles with spins that have rotational symmetry. And that's exactly the trapped ion system here. So you have these 27 trapped ion qubits all in one dimension. And these qubits spins, they're kind of the same thing. Also, we can use lasers to create things like magnetic fields and interactions between the spins. And one key element of this experiment is that the interactions between the spins are long-ranged, meaning spins can feel other spins that are far apart. So in the past quantum simulation experiments using trapped ions, people used one big fat beam to shine all ions at once. And we could see only somewhat short-range interactions there. However, now we have the ability to shine lasers on these ions individually. And this makes the ions physically vibrate in a collective way, so the ions can feel other ions even if the other ion is far apart. And that makes this long-range interactions possible. So how the experiment works is, first you only have the magnetic fields, and then you slowly ramp up the long-range interactions while decreasing the magnetic field. Then you measure all the spin values and see how correlated they are to other spins. And the result was that all these long-range correlations survive, even for spins that are super far apart. And this long-range correlation is a key feature for breaking the continuous rotation symmetry. So this work showed that they can physically create this one-dimensional quantum system with long-range interactions. And this is a system that theorists have been studying for quite some time to look at where symmetry breaks. Or in other words, what kind of quantum phases there are in this system. It's fascinating that those theoretical results can now be actually seen in a physically built quantum system. And of course, with this actual system, you can push things further. So inspiring physicists to come up with new theories and verify again with other experiments and so on.
Yeah, that's awesome. But that's not all in trapped ions, right?
Yeah, there was also this second paper by the University of Innsbruck team. This work also uses their trapped ion system to explore a very interesting theory on quantum entanglement. Entanglement is, of course, the most mysterious phenomenon in quantum physics, and people have been trying to understand entanglement in quantum systems. There are questions like, how does the entanglement grow as you increase the system size? How is it different between ground states and excited states? And of course, there are so many challenges on the experimental side as well. How do you measure entanglement? How do you prepare ground and excited states in the first place? And this paper beautifully combines all those theoretical and experimental questions. What's interesting to me is that they started from this old theorem from the 70s, namely the Bisognano-Wickman theorem, and this was in quantum field theory. It makes predictions about the entanglement structure of the vacuum state of our space-time. Then there is a conjecture that this theorem can be applied to a system of interacting spins. So the entanglement structure of the space-time's vacuum state can be translated to the entanglement structure of the ground state of a Hamiltonian. Now, this is yet a conjecture, and probably the math behind it is very, very hard. But before proving it, we can now see this on an actual physical system, because as I explained before in the previous paper, these systems of interacting spins can be mapped to trapped ions.
Now for experiments, the problem is that we can't just measure anything that we want in a system. The information that we can get from trapped ions is limited. You can only tell whether each spin is in the up state or down state at the final moment, and this is just a property of quantum measurements. So the Innsbruck team and their collaborating theorists have come up with clever tricks to measure the entanglement of a subsystem. They call this trick the entanglement Hamiltonian tomography.
And the experimental setup they have is a one-dimensional chain of 51 trapped ion qubits. And again, using lasers, they created the system where each spin only interacts with its left and right neighbors. Then because they have so many ions, 51, they can increase the size of the subsystem and see how the entanglement grows. They show that for states that are near the ground state, the entanglement stays roughly constant with the subsystem size, but for heated states, the entanglement grows linearly, which agrees with the theoretical predictions. They also looked at something called the entanglement temperature, which is related to the Bisognano-Wickman theorem. They showed that for ground states, the temperature has this parabolic profile along the subsystem, but for excited states, the profile is much more flat. And this again agrees with the spin version conjecture of that theorem. And another interesting aspect is that they used the VQE, or variational quantum eigensolver, to prepare the low energy and high energy states of the spin Hamiltonian. Probably you may heard of VQE as an algorithm for calculating the ground state energy of a small molecule in small quantum computers. And it's amazing that they modified this algorithm for physically preparing the near ground states and heated states in an actual quantum simulator. Of course, there are a lot more than what I described in this paper, so check out if you're interested. And together with the previous paper by Duke, I think these works are very interesting in that they check theories about quantum matter and entanglement on an actual quantum hardware. So we're actually in an era where theoretical calculations and quantum simulations are both tools for making scientific discoveries. And I really like this back and forth between theory and experiments. And I hope to see it more to push the frontier of what we know about quantum.
Moving on. So neutral atoms are on the roll, and the scientists at Harvard, MIT, and Quetta Computing just put out another head-turner of a paper, this time on logical qubits implemented in neutral atoms. And there are some tall claims here, which we want to study and explain in detail next month. But the authors have basically reportedly realized a quantum processor with logical qubits made up of 280 physical atomic qubits, and shown the steps for error correction on 40 logical qubits, which they call color codes. At the time of recording, the journal Nature has put out the paper as an accelerated article preview, which means that it was accepted but still undergoing editing. So the content could be changing. And there's some reviews from the scientific community that potentially still needs to be addressed, so we'll keep a close eye on this paper over the next month and cover it in detail when we have all the pieces. Now, onto the final news and a truly spectacular achievement. NASA Jet Propulsion Lab scientists and their collaborators have achieved several milestones in performing ultra-cold atomic physics experiments in space. Ultra-cold atomic experiments try to answer questions about the fundamental physics by studying the interaction between matter and light. They have implications for quantum computing too, mainly trapped ions and neutral atoms. Now, these experiments are challenging enough to build and precisely control in a lab here on Earth. Trust me, I know. Especially achieving a Bose-Einstein condensate, or BEC, which is a true technical feat. A BEC is an exotic quantum state of matter formed when some kinds of particles are cooled to temperatures close to absolute zero. Imagine how much harder it would be to do that in space. Yet, that's what these scientists have done, create a BEC out of two different types of atoms up in the International Space Station. It's insane how far we've come with AMO technology and space technology. Now, why do we care about doing these experiments in space? It's because we can study compelling physics questions where Earth's gravitational pull is mostly eliminated. This includes testing the theory of gravity itself, or studying quantum chemistry and quantum mechanics. You remember that famous experiment Galileo did to show that heavy and light objects fall at the same rate when you eliminate air resistance? So gravity accelerates all matter by the same amount. Except, what if there are tiny fluctuations in this behavior at the atomic scale? That could possibly upend Einstein's theory of general relativity, which makes it really exciting to study the quantum interactions between different species of atoms. But we need very precise experiments with ultra-cold atoms to reveal this. That's why this dual BEC experiment in space is so fascinating, and NASA did that with rubidium and potassium. They made several hardware upgrades to their cold atom lab that's already up in the International Space Station, including installing a microwave source to cool their potassium atoms. And they tweaked their experimental parameters until they created a simultaneous BEC of both rubidium-87 and potassium-41. This really shows that they have phenomenal control over atoms up in space, and this paves the way for understanding fundamental physics that we cannot explore down here on Earth. It's so crazy.
Yeah, that's amazing. So well, that was quite a lot of great news in the quantum field, and that's it for this month.
Thank you for tuning in to our Quantum News Monthly Show. Make sure to subscribe, and we'll see you in the next year. All right.
Oh,
We.
that was...
I hope it was recording.
Oh, shit.
Imagine.